Yes, so today we are going to talk about this paper, and this is the Jerry Chaperon is conduct this research, and he actually is the director of the University of New Moscow Center, and his acts of research include the high temperature and the low temperature geological process, and particularly for the higher precision isotope measurements for the trip oxygen isotope of oxygen. So next paragraph, next page. Yes, so the first author is Jessis, and he's a master student, and his advisor is the Jerry Chaperon. And so next, let's start it from a question. So please move to next point. So the question is how to estimate the Earth's surface temperature, and particularly the ocean temperature in deep time. So it's really an important question because the ocean temperature is one of the most important parameters that's constructing the habitable Earth. So oxygen isotope composition of a king sedimentary chains are usually used to constrain the ocean temperature in deep time, particularly for the king area. So please move to next. And actually, the rationale is that the fluctuation of the oxygen isotope between, for example, the silicate and water is temperature dependent. That's why it can be used to constrain the ocean temperature in deep time. So next, I will give an example here. So please move to next paragraph. And this is figure. You can see that the y-axis is the fluctuation between the cabinet and water. The x-axis is temperature. We can see that the fluctuation between the two phases is called wheel with temperature. That's why the studies, the research use this oxygen isotope to constrain the temperature. So please move to next paragraph. But the problem is that and the delta 18 value of Asian water is poorly estimated, and also the post-depositional digest will affect the delta 18 value. And this causes two distinct opinions about the ocean temperature. For example, please move to next paragraph. And we can see this is the published paper in 2017, but in GPL, and also just use the delta 18 oxygen value of the cheese to constrain the ocean temperature. The figure A shows the time series of actually I think this delta 18 oxygen value of cheese oxygen stops and also just constrain the temperature. And we can see that the ocean temperature for the Archean is pretty higher, maybe 70 or more. And in another research, please move. And we can see this is a self-consistent geological carbon model. And also proposed that the ocean temperature in Archean may be similar to modern ocean. And the temperature may be 0 to 50 degrees. But anyway, we can see that there's like pretty conflicts about this ocean temperature in deep time. So in this study, they also just try to use the trip oxygen isotopes, particularly delta 18 and capital delta 17. So in fact, as a matter of fact, they also just introduce a new isotope that is the oxygen 17 in this system, and the capital delta oxygen 17 is copied by delta 17 and delta 18. The target is that they also try to constrain the oxygen isotope values of Archean ocean, they have to constrain these parameters if you want to constrain the ocean temperature. So they also just use the mass balance model. So the concept of this model is that the oxygen isotope composition of the ocean is buffered by higher low temperature process. And more specifically, we can see that this geologic process includes, and please move, includes the higher and low temperature alteration of oceanic crust, and also weathering of continents and continental growth by sedimentary recycling and mantle recycling of subjective water. And please move. So this figure try to illustrate how this oxygen isotope composition are affected by the higher and lower alteration flux. And please move. So we can see that this is the lower temperature altitude basalts from the DSTP program. It means that these basalts react with the seawater at low temperature, and also just I think the sample is compiled by the author from previous studies, and this is true that the high temperature altitude basalt from LTP program. And please move. And these are the experimental raw products of basalt reacted with seawater at pretty higher temperature. And we can see that for the high temperature, the capital, the delta 18 value tends to decrease, and the capital delta 70 value tends to increase. And for the low temperature, we can see that the influence is converse. So please move. So please move to next paragraph. Yes. Okay. This is the ecological samples from the Roberts Victor Kimberlite at South Africa, which has a protolith age of 3.1 billion of years ago. And according to previous studies by other researchers, and it preserves the oxygen isotope composition of a key oceanic protolith. It means that these ecological samples react with these ancient ocean, and it preserved the oxygen isotope composition at that time. And please move. And the author points out that the oxygen isotope composition of these ecological samples overlap with the modern oceanic samples. So the author just proposed that the Archean oceans have similar isotope values as today. And for this question, we have to look at other researchers to whether the oxygen isotope composition of Archean ocean was lower than modern ocean. So I just show an example here. This is the Archean cheese data 18 values. You can see that the Archean cheese just presents lower data 18 value compared to modern samples. The one explanation is that the lower ancient or lower Archean ocean oxygen isotope composition caused these lower data 18 values of Archean cheese. So in this paper, they also try to test this hypothesis. So please move. And they also use the mass balance model to test this hypothesis. And this figure is the evolving seawater conditions with varying higher temperature elevation and continental weathering flux. So please move. We can see that if you want to get a lighter Archean ocean oxygen isotopes, you have to get a lower height, get a lower. This here is higher temperature elevation flux and higher content weathering flux. But actually, and also, so how to get this such lower and higher flux in this paper? They also just point out that in the deep time, please move in the deep time. In deep time, the lower sea levels or the great rate of sea floor spreading caused the lower high temperature elevation flux. Please move, and higher carbon dioxide pressure and easily wet greenstones cause the higher continental weathering flux. But actually, if it's right, you can see that, for example, the high temperature elevation flux is pretty low, and we can see that. Please move. We can get a pretty low data 18 values as seawater oxygen isotope values, and is inconsistent with previous constraints of ocean isotopes. So maybe yes, okay. So in the end, they also try to constrain the Archean ocean temperature. So in the first place, they also just to try to change these two, the high temperature elevation flux and the continental weathering flux to get the ocean isotope composition of the ancient ocean. So based on this, as we discussed above, the oxygen fractionation between silicate water is temperature dependent. So it means that if you have oxygen isotope composition of the ocean, and you could calculate the oxygen isotope of silica that equilibrium with seawater at certain temperature. So we can see this curve. Okay, I could back to yes. So this curve is calculate the equilibrium silica and water fractionation curves. But we have to, so if you get the theoretical curve, and please move, and also just compiled the Archean chip samples from previous studies, and we can see that there are some samples just close to the equilibrium curve. They also just point out that this Archean chase just equilibrium with seawater during precipitation at that time, and for other samples they are not equilibrium with seawater. So I'll use these samples. Sorry, they could just back to yes. So use these samples. They could calculate the equilibrium temperature of the ocean. That means from 80 to 120 degrees. Here, I have to give comments here, and that the temperature got here is only from the oxygen, isotope system. If you use another, isotope system, you will get another temperature may be higher or lower. So we have to know that. So please move to next. So this is take-home message. So firstly, they also try to emphasize that the oxygen isotope composition of the ocean is buffered by higher and lower temperature geological process. And second, the trip oxygen isotope composition may provide new insight into the ocean temperature in Archean. So that's all. Thank you.
Okay, thank you, Chuntao. So, questions from our participants today? Okay. So if they're right, then the very high temperature in the Archean Ocean, I would expect that's very fast precipitation in the Archean, because when water goes 80 degrees C, then that means that evaporation will be very, very efficient. So does that also mean that for the Archean, if they are right, if this scenario is the case, so does that mean the Archean land weathering will also be very efficient? Because you think about the precipitation will be, evaporation will be very efficient, and so that's likely the precipitation. So that means we will have a raining, very rainy Archean.
Yeah, maybe. Yes, but
of course without much plants, because in the Archean, if so far as my recollection, that
there's no plants. There's no plants in Archean. Yes, if it's but actually it's controversial because you can see that there's a lot of hypotheses or assumptions during this research. So, for example, they assume that the Archean Ocean isotope composition is similar to modern ocean, but actually, this is wrong. Maybe it's not other opinion about this problem. And also, we can see other research. For example, the last I think maybe I just put some additional yeah. 39.
Okay.
Yes, this is other research, and yes. So in rationale or essentially the fractionation between the ocean. Actually, let's see. The oxygen isotope composition of these Archean cheese or other medium carbonatites. The oxygen isotope of these sedimentary rocks is determined by the temperature and also the oxygen isotope composition of the ocean. And this research used the iron oxides, and this sample is really different because you could see the figure B. You can see that the fractionation between and the iron oxides and water, the capital delta is constant with the increase or decrease of temperature. And they also just proposed that, and also you can see the right figure, and they compiled the different iron oxide samples. You can see that the iron oxide samples, the oxygen, this delta 18 is gradually increase with time. And if it's not influenced by the temperature, and this increased trend should be inherited from the ocean, or from the equilibrium with the seawater. So in this paper, they also just proposed that the oxygen isotope of the ocean composition is not constant, or specifically not similar to modern ocean. So yes, it's really controversial for this topic. So, but this also did not cite this paper and did not consider other situation. And the hypothesis or the assumption of this paper is only cited from one ecologized samples. That means the 3.1 billions of years ago. Just use this one sample, one location sample to give the assumption. So maybe it's not very suitable for this assumption, I think.
Yeah, let's see how the speaker deal with this question on Wednesday.
Yeah.
Okay, so it's interesting too, because for obviously for this Galilei paper, as the users here, they have a team of more influential people in the community, the sedimentary geochemistry.
Yeah.
Okay. But for it's interesting. I don't know whether there are people study the modern diagenesis sedimentary process to see that how does the oxygen isotopes are fractionated between the different minerals.
Actually, most of the sedimentary, most of samples oxygen isotope fractionation between the sedimentary rocks and the seawater is time dependent. Most of them is time dependent, and this also just to find the iron oxidized sample to is pretty distinct. So that's why you could publish in Science. So it's not maybe it's a bit difficult to get those samples. And this figure A and B is doing, I think, this experiment results in the laboratory. Experiment result in laboratory.
Yeah, I think so. And yes, it's practical to do this in the laboratory. And I think it's also quite interesting to see that people are beginning to do this. So you buy some solutions in the laboratory and then you begin to do them. So then you get a solution in the time series as what you would like to put in days, weeks, or months. And then you measure the isotope, stable isotope compositions, because if the temperature is relatively low, we will calculate from the kinetics that it take a very long how long that is it will take long for them to reach equilibrium. And so people have although I'm not expert on this, but I've already seen people doing this, especially since the stable isotope measurement is more available nowadays. So there are more and more people doing this in their laboratory. It's quite a cost-effective way of running some experiments, depending on the isotopic systems or the solution chemistry that people are interested in, especially for earth scientists that we're looking for some, like say for different scenarios. Of course, the solution compositions could really vary a lot. Yeah, I don't know about Archean Ocean. I don't know what's their pH, for example, are they the same? And a lot of water chemistry could be different.
Yeah, some model have calculated the temperature. As I showed in the, I think in the PPT, in the PowerPoint, I think maybe, yeah, 11. Yes, 11. So yes, this is the temperature, and they just use the geological carbon cycle model to calculate the temperature of the Archean Ocean. And actually, in this paper, they also calculate the pH and other parameters of the Archean Ocean. And I could share. I think I could share this paper, and you see the pH of this paper.
Any other questions from other participants today?
Okay, you can see this is the ocean temperature here. Maybe lower in the past. Actually, these parameters are they have relationship between temperature and the pH and also the carbon dioxide. So we just use the model to calculate this. I think this is the model, carbonate and silicate weathering model. Yes.
Okay, it's interesting because this is a relatively simple let's say model, because our Archean, people don't know about for example, land proportion very well. People don't know what's the topography at that time, because for the modern Earth carbon cycle system, then there are relatively mature system codes that are available for people to calculate the effects of the, let's say, different carbon, and finally on your surface temperature. So of course people could consider more complex ocean models. So for this Archean ones, I think it's probably relatively simple because people don't understand even some of the basic things like the ocean temperature. But now the modern Earth, we measure it pretty well. And also for the Archean, let's say, even the surface temperature itself, let's say, of course, ocean water temperature by itself is very important. And so does the mantle potential temperature. Also, what the people would generally agree is that mantle temperature is about 200 degrees higher than our more mantle potential temperature. So if I'm going to make a bet, I would say, okay, of course, Archean temperature is higher, but how high? I need some more evidence. Okay, let's see the chat. Okay, any more questions from our participants today? So if not, could everyone open your video for 20 seconds before we turn the meeting off? Since several students are staying in their own dormitory, then basically we could see how your dormitory looks like. Okay. Okay, that's about it. Have a good week, everyone. I hope that you're enjoying your different places now. Okay, since Wangsi has the warmest weather, Wangsi is in Guangzhou, and that's she's still wearing shorts. So it's really in the southern part. Okay.
Okay, bye.
Bye bye.